A choice right now, between fear and love. It's just a ride.
Out of the dark night of ignorance and into the shining light of truth.
Expanding reality.
A population of citizens capable of critical thinking.
We don't see things as they are, we see them as we are.
There's a level of reality where everything dissolves into an ocean of energy.
We empower our experience by insisting on our authenticity.
That's very profound. Very.
Expanding reality.
Welcome to Expanding Reality. I am your host, Brandon Thomas. So on this episode, we're going to talk to a good friend of mine. His career in aerospace engineering launched in 1982 with Rockwell International, working not only on the shuttle program, but on the STS-4 through 44, assisting on the Challenger accident investigation and the shuttle's return to flight as well. And he was just getting started. So from 1990 to 96, he was at Rocketdyne, where he worked on the conceptual design, planting, and implementation of the International Space Station and the electric power systems. So from there it was on to Boeing, where he continued to work and design development for the ISS. In 2003, he assisted in the Columbia accident investigation, trained astronauts for the ISS and spacewalks, performed zero-gravity aircraft experiments such as thermal vacuum testing, and he worked in the neutral buoyancy lab as well. His impressive accomplishments go on and on, but I'm not going to spoil it, because here today we have Curt Carlton, the man who kept his feet on the ground but his head way above the clouds. So Curt, how are you doing today, buddy?
I'm doing great. How
Good
about
deal.
you?
Oh, every day above ground's a good one, man. I appreciate it. Thank you.
It's more important for me because I'm a little older than you are.
No, that's okay. Yeah, all the days are great. Okay, well, Patrick, you're here as well. What's up, dude?
I am. How's it going?
Going great. How are you?
I'm good.
Okay, cool.
Doing very well.
And my brother Patrick as well decided to join us for this episode. You have an interest in this type of thing as well, don't you?
Quite a bit, yes.
Okay.
Quite a bit.
Do you want to tell us where your background lies?
Yes.
I didn't prepare a bio for you. I apologize.
That's okay. Not much to tell, but I did study astrophysics in college.
Okay.
Was very interested in exoplanets and followed NASA very closely and still continue to do so. I think it's very important. So very excited to be here for the conversation.
This is going to be great. So Curt and I have talked quite a few times on the phone, and I just found you incredibly interesting. We've become good friends, and I appreciate that. Your career is incredible. Your bio is insane. So let's just begin at the beginning. So what got you interested in aerospace engineering to begin with?
Like anybody going to college, you never know exactly what you're going to take on or enjoy. But I always thought I would try and turn into a pilot. Tried to get into ROTC back in college, and nobody would ever guarantee you a path towards being a pilot.
Yeah.
They want you to join in and sign up for 6 years and, oh yeah, we'll do the best we can. It's like, nah, that's not good enough.
Yeah.
So headed into engineering, and Astro was the way to go back in the day. I went to school up at University of Washington in Seattle, and Boeing that's their home. So a lot of Boeing support went to the Astro school at University of Washington.
Oh, awesome.
And everybody that went there pretty much believed that they were going to end up at Boeing somewhere.
Yeah. And
just turned out when I graduated in 82, Boeing wasn't hiring anybody. Just time, the time of life.
Yeah.
And so we tried other things, and actually I just lucked out. We had on-campus interviews, after getting or just before I finished my degree. And I had an interview with Rockwell International, and the one line item on the whole, whenever you do an interview for college, they're writing down buzzwords that somebody can search in the corporation if they're looking for somebody. And my line was aircraft performance.
Oh,
because
wow.
I liked designing airplanes when I was in college, and I liked that part of the education.
Yeah.
And I put aircraft performance on there, and my first job was with the space shuttle, doing shuttle performance for the vehicle.
Yeah, because you got brought in right after college. So you graduated in 82. You got brought in straight to the program. And then your first thing that you worked on was, what was the fuel issue they were having with the shuttle?
They call it ascent performance, but they just, I jumped into the shuttle program right after STS-4, which was the first 4 test flights.
Right.
And the vehicle was flying different than they predicted or simulated.
Right.
So they wanted to figure out how to predict more like the vehicle was actually flying.
Yeah.
So we did what we called, flight design reconstruction. What can we do to the performance characteristics of the vehicle to get our simulation to fly actually like it's flying?
Right.
And the closer you can predict to actual, the better your margins are. Margins being just, fuel left over.
Right.
And if you can turn fuel left over into payload, and they always wanted to keep a specific margin that was safe.
Yeah.
So that it didn't run out of fuel. So they always had, this margin that was, you always wanted to hit. And it turned out we had more fuel at the end of the flight than we needed.
Wow.
So they wanted to take that difference and turn it into payload.
Yeah.
And it's a pound per pound at that point.
Absolutely.
At the end of the ascent trajectory, it's if you can turn that few thousand pounds of extra fuel into a few thousand pounds of payload.
Payload, yeah.
That's a bunch of money. So they're looking at it at dollars and cents, but we were looking at it as, how do we tweak all the variables of a, rocket and aerodynamic vehicle to make it to predict better, to simulate better.
So cool. So he was 26 when he was doing this. What were you doing at 26, Patrick?
I was teaching physics at a very small high school, so not that.
Okay.
Coincidentally, the same age Isaac Newton published all of his work. Albert Einstein published his work, so 26 seems to be a good age.
It's a good age. I was doing a lot of drugs and probably shouldn't have been doing that. But I did not have the ambitions you did. I did not know what I wanted to do. And so for you to just jump straight into it, just with even an interest in it, to be able to be thrown into that program.
Never really thought I would jump into the space program, so to speak, when I was going through college, but it was a great opportunity. And I got to say, I drug a couple friends with me, fraternity brothers from college. I jumped into Rockwell and got both of them hired the next year. And they loved it at the time. Early 80s is when computers were just getting going. Mm-hmm. And they just hired a bunch of kids because they wanted to take all this data and start using these great computers and start crunching data for whatever purpose. And it just turns out my niche was, shuttle ascent performance, and we just kept going from there.
And it's so cool because it started with just a glider program in 77, right? The late 70s, for sure, right after Apollo. And they just wanted to design a vehicle because after the Apollo program, they launched that Saturn V. They had all these vehicles that they used, but they weren't reusable at all. So it was a big waste of money, basically. If you look at it economically. And so what they wanted to do is make a mostly reusable space vehicle.
Correct.
And so that's where they came up with the shuttle program. And you got on board it in 82, and the first launch with Columbia was in 81.
Correct.
That's crazy. So you're a year into the program even being done as a manned flight program, because Endeavour just was an unmanned glider program, or it was manned, but it was just a glider program. And then in 81, that's when they launched what, just a pilot and a co-pilot?
Two-man crew, pilot,
instead of
co-pilot.
the 8 that they normally had?
And it could vary anywhere in there depending on, the mission objectives, but up to 7.
So you got in at basically the damn ground floor, maybe the second floor of this.
And it was, at the time you don't even realize how awesome that was. And then hung with it through the end of the shuttle program, which is, in 2011. So that was 30 years later.
Yeah.
And who thought you could be able to hang on a program that long and do what you want to do? But it was a great ride. I talked to people about what I used to do, and they're going, really?
No, it's incredibly fascinating. And like I said, we've had a couple of phone conversations. I think the first one I was just like, hey, just do a 10-minute little, would you like to come on the show? We ended up 45 minutes later talking. The next time we talked for about an hour and a half. I think your phone died, and then you called me back on your wife's phone, and we continued the conversation. So this is awesome. I've been wanting to get you on for a long time here. I know Patrick drove all the way up from Austin here just to speak with you. So we're incredibly interested in what you have to say. So with the shuttle program, the first challenge that you achieved achieved was the fuel or the asset issue that you guys achieved at the age of 26. I feel that the listeners and viewers really need to know that.
I started at 22.
Oh, no big deal. No big deal. My bad.
It was straight out of college, but
that's fascinating.
And yeah, jumped in early, and as the shuttle started to develop into a business, a lot of the work that NASA was doing started getting centralized in Houston. So we moved to Houston, and they started what they called the Shuttle Operations Program, which was, the intent was figure out how to bring in customers, who had a payload of whatever it was, and be able to put it into the shuttle, combine it into the shuttle, work it out so that they could meet their objectives on any given mission that we had. So you're fitting payloads into what missions you were flying and what they were doing, what other things were flying. They couldn't interfere with one another. And
yeah, because that was the way that they subsidized the cost of the launching, was they had private entities that wanted to do space. They launched satellites up there. The government wanted it because STS stands for what? Space Transportation System?
Correct.
And so they were just wanting to get payloads up there, and people paid them to do it, which subsidized the cost quite a bit.
Correct. And, a lot of them were satellites. We had Hubble Space Telescope.
Yeah.
You had Intelsat, you had the GPS systems were in there. I mean, it was whatever you want to do. And then many small payloads, they would just they had these things that were basically, I think they called them gas cans, but they were basically this canister you'd mount on the inside of the payload bay. And when the payload bay doors opened, they started collecting data, whatever they wanted to do.
Wow.
And a lot of times they'd expose themselves to vacuum. And that's what they wanted, was the vacuum of space, and do whatever their experiment was. And what you're trying to do is minimize their cost,
right,
to make this happen, to get whatever they want to do. So there was lots of things. And it turns out lots of experiments that we did on the space shuttle were intended to test out capabilities for space station for the next step.
Right, because you helped aid and design that.
Well, and you want to, with any program, you want to learn from your past, whatever. And I jumped in on the ground floor space station, early 90s, late 80s. And you always wanted to test out everything you could with the shuttle when it's there.
Yeah.
If you've got something on orbit and you have a primary payload that's, let's just say launching a satellite or doing whatever, there's still a bunch of room left in the payload bay. And you put up an experiment up there that tests out some small piece of what you're trying to accomplish. And the hardest things with space is you got to work between, if you're on orbit, on space station, as an example, I mean, you're working in environments that are minus 200 degrees F up to plus 250 degrees F.
Yeah.
So
and sunlight and shadow type thing.
Right. When you get on the dark side of the Earth, everything gets really cold. When you get onto the sun side of an orbit, everything gets hot.
Yeah.
And everything's mechanical. I mean, everything we do is mechanical, and mechanisms don't work good in that environment.
Yeah. It's hard to simulate that on Earth as well, because there's extreme conditions, and especially incorporating a vacuum. It's
not hard to do, but I mean, you can usually only do it in, small environments.
Right.
It's not like you can, NASA has some facilities that are rather large, and we have some facilities you can actually put an astronaut in a spacesuit into a chamber, and that chamber can go through those temperature swings.
Wow.
And we did that kind of testing as well, where you put your mechanism into that environment, and then you put the man in the loop. And if he's supposed to do something to actuate it, deploy it, assemble it, whatever you need to do, he would try and actually do that in that cold and hot environment. And they use that for certification of hardware.
Yeah.
Just making sure that your mechanisms are designed. And the funny part is that you get down to problems that are created when your dimensions are off by 1/1000th of an inch.
Right.
It's like anything. You get moving mechanisms, and even metals shrink and grow at extreme temperatures.
Yeah.
So if you have a telescoping system, if those features aren't designed and controlled to very tight tolerances, they'll freeze up in cold temperatures, or they'll get too loose in hot temperatures. Or you just have to, if your mechanism doesn't work at extreme colds, you wait 30 minutes until the sun hits it, then it warms up, and then it starts working again.
See, there was a movie that I saw. I can't remember the damn movie, but they were putting something on the shuttle, I believe, and that was one of the issues they were having. And this, Hollywood film or whatever. But there was a bolt that wouldn't fit, and he goes, "Oh, just wait." And when they came around to the sun side, it heated it up enough, and then they were able to implement it. So that's a factual thing.
That happens all the time.
That's fascinating.
Yeah,
so there is a time in the orbit process to where you're just like, oh, just wait a little bit, and then we'll reach around the other side and it'll work.
Yeah, space station orbits the Earth every 90 minutes.
Wow.
And in that 90 minutes, about 30 of it, or 35 minutes usually, is in darkness and cold. And then you come out to a sunrise and you come down to a sunset about an hour later. So you get about an hour of sunlight and about 30 minutes of darkness every orbit.
What long-term effects does that have on a craft that's constantly ebbing and flowing?
And that's what you have to protect or design for, so that doesn't affect, so that the vehicle's not affected by that.
That's fascinating.
And that's usually whether you're building a big mechanism or a small mechanism, and I hate to use the word, but everything is a mechanism. Even if it's just a piece of truss, a piece of steel. Yeah. It can twist, it can turn, it'll shrink and grow, and if it's not properly designed, it could create a problem.
Yeah.
I mean, they put a basically railroad track on space station that the mobile transporter cruises up and down.
Oh wow.
So it's about 200 feet long, but it's a train track. So, and those tracks constantly shrink and grow.
Yeah.
So the wheel bearings that they put on the, basically the train that runs up and down has to be forgiving to that shrinking and growing.
Just every bit of it's fascinating. Even those environmental challenges that you go against. That's incredible.
It's late in my career. You know what a ball detent is?
No.
It's
ball detent, Patrick?
It's just anything that you use on like on a cabinet door latch.
Oh, okay.
It's a small little cylinder that has threads on the outside, and there's a ball in it that's spring-loaded. So if you need a little latch,
yes,
on a door or on anything, it's a very common part for getting a soft capture, so to speak.
Okay.
Very common part. We use them everywhere on space station. 15 years into the program, we start having problems, and we can't figure out why. So these little ball detents, the ones we use in space, they're all stainless steel. They're all relatively highly controlled. And I called the vendor, and the vendor was blown away that we used them on space station.
It's like, no, man, this goes in your house.
We never tested those to cold temperatures before. And I'm going, oh, you're kidding me.
But I'm sure somebody thought of that before they threw them up on the space station, right?
Nobody.
That slipped by, huh?
Nobody. And the hard thing is you're constantly using existing design.
Sure.
You use a certified design so that you don't have to go back and start from scratch.
Okay.
So I don't know how this one actually got in, but they had only tested to like just below, zero, freezing to zero. That's where they did that for uses in like, freezers and that are on that kind of range, but they never went below to the high negatives or the low negatives. And when I told them we were operating these things at minus 200, they're going, how are they working? I'm going, no, that's why I called you.
Because they're not. But for 15 years, they did okay?
We had a couple of problems with some devices. We had one pretty serious one early on that we launched something in between the railroad track that was going to be removed and assembled.
Okay.
But that was just a convenient spot to mount it. And it turned out on orbit, we couldn't get it off.
Oh, no.
So that ball detent stuck and prevented this thing from being demated, so to speak, or taken apart. And it was stuck there. So, we went out and hit it with a hammer until we got it out. But it was...
I like that there's still a lot of practical knowledge that goes involved up there. A lot of like, well, it's what we got.
And you try, you let it get to the hot side of the orbit, and if it loosens up and it works, you're good.
Yeah.
If that doesn't work, you get out there with a pry bar or a hammer and make it work.
So there's that old joke that there's things on the space station and the shuttle are like $10,000 for a hammer and like $40,000 for a toilet seat. What's that all about?
It's true. It does cost that much, but typically the cost is associated with kind of what I just mentioned to you. You have to certify it to work in any environment.
Right.
And so typically it can't be cast.
Okay.
Because when you use a cast material, it has bubbles or voids in it.
Mm-hmm.
When you take a void to vacuum, it basically will crack the material.
Who found that out first? They're up there trying to...
You see that all the time.
Okay.
I mean, any early testing, if you just put a Craftsman wrench in a vacuum, it'll probably break when you go to vacuum and cold.
Got you.
I mean, and it'll just fracture.
Yeah.
So, I mean, that material just can't handle that kind of environment. You also don't use anything that's coated. So like chrome plated, you don't want to do that because that will also have a void underneath it. And when you take that to vacuum, that will just crack your finish.
Yeah.
And if you don't crack the material, it'll be the finish, and that creates a sharp edge. All that's bad.
Problematic, yeah.
All that's bad when you're talking about a guy in a spacesuit, trying to make things work.
Yeah.
And but I mean, all that comes with time. But back to the ball detent, everybody thought it was good, and I'm sure in the environment that somebody wanted to use it in, it was good, but it shouldn't have been outside without going through additional testing. And a lot of times you'll use something and you'll test it and you're going, well, I'm really not going to get down to minus 200. My environment, we're going to put an astronaut in that environment, is probably only going to get down to like minus 40 or 50.
Right.
And it still works at minus 40 or 50. But once you start going beyond, it gives you problems. And that was just one of those things that I dug up that was just, I hate to call it funny, but it was
funny.
It's like, how did
Nice
we
little
never know
oversight.
this?
Yeah.
How did we never know this? And don't get me wrong, whenever you wanted one of these little ball detents, you only went to this particular vendor.
Yeah.
The vendor's name is Vleer. I don't mind using it.
It's a good plug because they probably put this on their website. We're on the ISS. We're good.
We're good.
Down at negative 200. It's on their bio right now. If not, they should be.
And I helped design a tool that they used on space station that had a couple of ball detents on it.
Okay.
So we had the full range of information on this one particular, they were smaller detents. They come, as big as your thumb and as small as a pencil. So, I mean, they're all kinds of different sizes, but this particular one that we tried, we tested and it worked fine all the way through hot. But as soon as we got to about minus 40 and beyond, it started freezing up.
Damn.
And when it frees up, that basically means that little soft capture doesn't want to release.
Right.
So the ball detent, the spring doesn't work, the thing doesn't work, and it won't come off. And then we got into a lot more detail about how they manufactured it and how they made the ball captive.
Yeah.
And it turns out, they basically just cut a tube, and that little crimp created the captive nature of the ball. And that process wasn't really quality control.
Yeah.
Right.
Yeah.
I mean, it's we cut it there and it keeps it captive by this, and then we stop there. And it's like, well, how close was it? And how much did you deform the cylinder that you did when you cut? And it was always good enough. You know?
Because it wasn't meant to be used on the space station, man. That's pretty cool, though.
It wasn't meant. I don't want to say it wasn't meant to be used. It met all the right material requirements.
Just not at negative 200.
It just
It was just a temperature issue.
At those extremes,
Yeah.
right? It just it froze up at the really cold extremes. But once it warmed back up, it worked fine again.
Just wait a minute. It'll be fine.
And
You're stuck out there for a minute, Glenn. Just give it a minute. We'll be around in 35, and we'll free you up here. When you get assigned a project, is this something that so the projects that you worked on included mechanisms like this and tools that you designed for space, and then you watch tolerances and materials, lack of coating, things like that. Whenever you got a project, did they come to you with this, or was this somebody that did you figure out anything where you're like, hey, we can do this better? And then you improve on a design that's already there?
You do a lot of improving on anything, but most of the projects that we worked on, and one of the very cool things about working on the space shuttle or the space station is it was first of a kind stuff.
Mm-hmm.
If you build a tool, it's a special purpose tool. No one's ever done it before. you're pretty much starting with a blank piece of paper.
Yeah, you're not shipping a bunch of those IKEA wrenches up there that'll do everything.
And you're just doing the best you can,
Right.
trying to figure out what the problem is, making a tool or a solution to fix your problem.
Right.
And you get to cradle to grave it, which was the part I always liked. You start with the problem and you try and fix the problem, and then you get to come up with some concepts of how you want to fix it, and then you run it by a bunch of people and everybody goes, okay, yeah, we like that one.
Yeah.
Go forward with that one. And then you get to, I don't really design the whole thing.
Mm-hmm.
I worked more on the conceptual side. Then we hire, drafters, technicians, designers to actually build it.
Yeah.
Or design it, and then you have somebody manufacture it, and then I usually got back into the projects when we had to test them.
Right.
If it was a astronaut in the loop, my job was to get that astronaut to understand how the tool worked, make sure that the tool worked with his suit,
Right.
and that he could understand how to do it, and he didn't run into problems with it, and could install it, assemble it, do whatever he needed to do with it.
Yeah.
So there was always that hands-on purpose.
Mm-hmm.
And I'd say that was pretty much my niche in life, was, building simulators of the actual flight configurations, and then putting it in front of astronauts to, first of all, agree that it worked and agree they could do it, and then being able to certify it that it would work in the extreme environments, and then putting those two together to have the astronaut in the extreme environment actually working the tools or working the mechanisms. And it was, it's really enjoyable. And I did this with the space station as a big project, but the small goals in life is, that's the little things that keep you going.
Yeah.
The little projects, and and you were able to start from a blank piece of paper, get it agreed to, get it designed, then we test it, then the manufacturer will start building a bunch of them, and you got to test each one as it comes through the pipe to make sure that
no imperfections.
He's got quality control that won't hurt anything.
Yeah, the consistency across the process.
Yeah.
What was your favorite project that you worked on in your 40 years?
Favorite project. After the Columbia accident, the Columbia accident is where they had a breach of the heat shield protection system during entry, and that caused the destruction of the vehicle.
Right.
And the heat shields on the shuttle are made of what's called a silica tile. It's basically a porcelain kind of tile, a very lightweight, ceramic kind of a tile.
Right.
And the material, the silica material, is if you hit some of these tiles, it would basically fracture like a tile that's on your floor.
Yeah.
And one of the natures of this material is nothing sticks to it.
Oh, okay.
So the challenge we had was to fix a damaged tile. So if something hit the tile during ascent and it was damaged for the whole flight and you didn't know it, but you saw it, somehow you identified the problem on orbit, and they said, oh, well, we got to do something like that in order to get home. So we were part of developing systems associated with how can we get an astronaut out there? What kind of material can you create that actually sticks to silica tile?
Yeah.
And on the ground, that kind of stuff's easy. You go out and get a caulk tube and you
Gorilla Glue or something. Yeah.
Squirt something in there and it dries and we're good.
Yeah.
Well, it doesn't work that way at cold and hot temperatures. It doesn't work that way in a vacuum. So you had to figure out chemicals that will give you a chemical reaction that will actually cure and harden. And then you got to figure out some way to get it to actually stick to this tile that doesn't want it to stick to anything.
Right.
And after the Columbia accident, we got involved in a number of very interesting small projects to enable a crew member to go fix the damage to the bottom of the shuttle.
Right. And that was the second major disaster that happened. It's 133 successful missions in 30 years with the shuttle program. And the accidents you had were the Challenger in 86 and then the Columbia in 2003, which is what you're talking about there. And that specific instance is when, I guess it was a piece of foam or debris on launch that happened and it hit the underside of the left wing, that's what made it fail on re-entry, was it just it couldn't, structural integrity, it couldn't work.
Well, and nobody knew it was there. I mean, they flew that whole mission, and no one realized that that launch environment created the problem.
Oh, okay.
So
yeah.
the guys on orbit didn't even know what happened.
So that was post where they were looking at grainy footage to figure out what hit and why, because they did definitely see temperature spike on the left side on reentry. And I think the captain even said we have 3 failing electronic sensors, temperature sensors on the left side. And that's kind of how they figured it out.
And, you know, coming in through reentry, it's basically a blowtorch.
Yeah.
You lost your thermal protection of these silica tiles.
Yep.
They're about 3 inches thick in most places. And that, you know, then behind that is just sheet aluminum.
Mm-hmm.
So, I mean, and at those temperatures, aluminum's just going to melt.
Yeah,
so
because the same thing
basically
happened.
what happened is you're going to get burn throughs.
Right, and then it compromises everything. You
And-
can't, one little chink in the armor.
And it just propagates.
Yeah.
You know, so the problem just gets worse and worse and worse.
Because the same thing I want to say was STS-71, where they did have a similar and actually a worse debris impact, but it was on the right side and it was not in the danger zone. It wasn't in a part that impacted that heavily on reentry, and so it wasn't a big deal. So it's all about placement and
It's there's so many variables in
Yeah.
there. But I mean, and again, if you're in a point on the vehicle where there's something behind that structural sheet of aluminum,
yeah.
then it's a problem. If there's nothing behind it, then hopefully it's not a very long period of time. You can just fly through it,
And it'll dissipate.
and or it won't create worse problems.
Right.
And if it gets bad enough, it just
Yeah.
burns through and just makes everything worse. But after that accident, I mean, the several challenges we had to work through. One was, the actual putting the goo, and it turned out to be, if you work on cars, there's a gasket goo that you make for gaskets that see the high temperature of an engine.
Yeah.
When you want to make your own gasket or you want to use a goo to put around a gasket, it's designed for hot temperatures. We used a compound very similar to that.
Okay.
Added some more fillers to it so that it could handle high heat, and then created a catalyst that would allow it to harden without oxygen.
Damn.
So it was like a 2-part epoxy that you put together, and they created fancy, compression guns that you could have this tank on your back, and you pull out your little hose, and it feeds these 2 chemicals to a nozzle that spirals it and mixes it as it goes through the nozzle, and then you fill, and you're done.
Damn.
And that particular system just got to be too complicated for an emergency repair.
Okay.
So you get all the way through it, and we ended up using a standard off-the-shelf caulk gun that just so happened to be made out of stainless steel. And the little cartridge tubes were made out of polyethylene, both materials which work in hot and cold environments, just coincidentally. So all they did is they created this 2-part mix in these off-the-shelf polyethylene tubes.
Yeah.
And you put a specific nozzle on the end of it that mixes the 2 chemicals together as it's coming out. It's just a little spiral in the nozzle, and you've created your system. So
you ended up just going down to Ace Hardware and picking one up and charging the taxpayers about $20,000 for that thing.
But we had to prove it worked.
Well, right. No. I know. That's the point I was trying to make.
The hard point of the cost is you have to go through all the requirements to make sure it's not too much force for the astronaut's hand.
Right.
There's no sharp edges on anything. When that stainless steel caulk gun is exposed to sunlight, that thing will heat up to 250 degrees in about 10 minutes.
Yeah.
So you got to make sure that it's not too hot for the crew member to grab in his gloved hand. And you got to put the whole off-the-shelf tool through all the testing.
Yes.
And then it's never off the shelf. They always modify it.
Oh, you have to.
Yeah. I need an on-off nozzle that on the ground is this, this tiny little thing you just flip with your thumb. But on orbit, this guy's wearing a spacesuit, and it's like wearing 3 pairs of garden gloves, and you got no feeling.
Right.
And they make a knob that's as big as a quarter for him to actually turn and actuate, as opposed to this little thumb switch of what it was originally designed as.
Easily articulated with our fingers, but in a spacesuit, it's much, much, much different.
So you always modify.
Yeah.
And then every time you modify, you got to prove that your modification didn't create a problem at
Right.
hot and cold extremes. So it's just a menagerie of, trying to do the best you can to pull it off the shelf, modifying it as needed, but not too much so that you don't create new problems,
Sure.
and then keep going. So that particular caulk gun with that particular can, I mean, I bought online and you can get it off the shelf for about $100.
Yeah.
But now to put it through all the testing and all the certification and all the quantities I have to burn to put it through the
Yes,
testing,
absolutely.
So
There you go, people. It's settled. He's told
Yeah.
you here. This is why those things cost so much. Quit hyper-focusing on it. It's not an off-the-shelf cost. It is a R&D type of investment in our astronauts.
And the hard part is always the certification. My job in designing and developing any kind of tools, you have this long laundry list of requirements, and you have to meet them all.
Sure.
And then after you meet them all, you got to go back and prove to people that you met them all. So all that has a series of testing or paperwork behind it that says, here's how I met that requirement. Here's how I met that requirement. Here's how I met that requirement. And you got to go through, we always went through a preliminary design review, a critical design review, and then we go through a design effort, and then you go through drawing reviews. And, NASA follows along at every step.
Right.
And in between all those steps, I get all the, in this case, Boeing engineers doing all the work to make sure they met all those requirements.
Yeah.
And then at the very end, you dump them a stack of paper that's 1,000 pages long that proved that you met every point. And that's what costs the money is, all the people, the time, the effort, the proof of the certification.
Yeah, and it's understandable. It's just one of those fun facts that everybody points to that, NASA $10,000 hammer, Well, of course it's going to be 10 grand, man. You got to figure this shit out.
There's a set of tools that the astronauts use on orbit.
Mm-hmm.
Excuse me, and they're primarily snap-on tools.
Oh, wow.
And the reason everybody
That's a good
loved
plug.
them is because they can make them out of stainless.
Yeah. And not coat them and meet the requirements.
That's it.
So was there somebody at Snap-on basically just going, yeah, we'll modify that for you? Or did you guys get a tool, modify and manufacture it yourself? You guys outsourced a lot of that stuff, right?
Typically, you buy it off the shelf. And
Interesting.
lots of tools, and we love the medical industry because all the medical tools are stainless.
Yeah.
Because they're associated with operations, right? And the scissors that the astronauts use, that actually always carry a pair of scissors in their spacesuit in case they get tangled or need to cut themselves out. They're an off-the-shelf pair of surgical scissors, and
Dangerous yet useful,
necessary.
Like you want it, you just don't want to put it back wrong.
right, it's necessary, and they have a specific pouch on their leg that's for that, and it's lanyarded to that pouch, but they can pull it out, do what they need to do, and then put it back in that pouch, and it's safe if you grab it correctly. You obviously don't cut your finger out,
You don't
like
wanna...
anything. It's a sharp knife. Don't do that.
Yeah,
But, you have to have it.
Right.
So, but we leaned on the surgical industry to actually, adopt that tool. They modified the handle a little bit so that you could fit with a big glove.
Yeah.
But the actual scissor itself was a standard, medical scissors.
Wow.
So, you always try and rely on anything that's already been designed.
Sure.
So that you don't have to. And lots of things are made out of stainless steel
Mm-hmm.
or other pure materials, anything that's a machined aluminum or, as long as the pedigree of the material is one material. And again, as long as cast things in general don't work very well. So they like them to be machined instead of cast, because cast introduce voids.
Got you.
But
so was working with the astronauts on their EVAs or the extravehicular activities, that's fascinating. So what was your favorite part about doing that?
And I would say the best part was the people.
Yeah, working with the guys and girls.
Yes, and it's always fun to, there's all kinds of different astronauts, but usually the ones that are spacewalkers, most of them are military background. Most of them are very hands-on. Some are PhD doctors, and a lot of the work that goes on with astronauts on space station is with doctors. So doctors that turned into astronauts, and then they do physiological, how the human body works in space.
Mm-hmm.
So while you're inside, you're doing a lot of testing. But with any astronaut, they've got 1,000 jobs, and from cleaning the bathrooms to walking through procedures and understanding the medical end of things that they're doing. I mean,
Yeah, you got to have a lot of tools in that chest, no matter what your specialty.
correct.
Because that was the thing that the space program, or the shuttle program specifically did bring, was that diversity in the space crews. Because before then, it was white males of military backgrounds, and that was the Gemini and Apollo missions, and the shuttle program is what allowed them to incorporate not only females but minorities as well. And that's when it started diversifying. That's why you didn't have to have so many military and specific. You could bring in doctors and engineers and PhDs.
You had to do a wide range of people to do the job.
Yeah.
And in a lot of cases, I would get a medical doctor that we're going to ask to turn wrenches. So you have to teach that guy how to turn wrenches.
With practical knowledge.
Yeah, and I mean, a military test pilot, he probably has his own sports car and works on it.
Right.
So you don't have to teach him how to turn wrenches.
Interesting.
But a doctor, and you'd always find a diverse person. There's lots of people that I'm the kind of person, I'm more hands-on.
Mm-hmm.
Right? You buy something, you get this installation instructions, you don't even read them, and you put it together. Right? And there are people who are complete opposite of that. They want the procedures. They want to read it thoroughly and read every page and understand the procedures and all the, the troubleshooting aspects of it and the gotchas as you're going through it. And there's people who like to read it first and then go and try it. And there's other people who just like to try it and figure it out.
Yeah.
And it's just a different mindset. And you'll find that most doctors are the kind that actually go through the procedure step by step before they ever do anything.
Makes sense, because there's dire consequences in their professions anyway, and they're used to being very methodical about the procedure.
And understanding everything thoroughly before you get into it.
Sure.
And like when you're working on a car, too often you'll just start taking things apart and putting them back together and, figuring out.
What are these extra bolts for?
Oh, did that work or not, But I mean, it's just a mindset.
Yeah.
So you have to work, and I worked with all kinds of people like that. I mean, all kinds of different backgrounds, all kinds of, different degrees.
Yeah, and that's what's interesting too, is you really had to tailor your teaching style. So you really had to kind of say, okay, with this particular person, I know I can give them this task and then turn them loose. I may need a little bit of tweaking here, but then with this person, I've got to be a little bit more extra attention just for the practical knowledge side of things. So you really had to tailor the situation to whoever you were talking to.
You tailor the way you train it to how the person learns.
Just sounds like such a cool job, man.
And
God, just the whole damn thing. Let's be honest.
It was a great career. It was, and again, because it was, one of a kind. It's not something that a guy would normally do. You teach them working in an environment, doing this thing, working a mechanism.
Yeah.
And it's typically it's this wholly over-designed mechanism, and you try and simplify it enough. Really what we're asking you to do is take that wrench and put it on bolt A, B, and C and turn it this many times until it's tight.
Yeah.
Now, can we reduce the whole mechanism and don't worry about what it does and how it works and all that. All we want you to do is put part A to part B and bolt them together.
Yeah. We figured out the rest for you.
Well, but that's what we're asking you to do. Don't worry so much about how this thing's going to perform and work in the future. Just focus on the task at hand, and not so much, that the antenna is going to work,
right?
Or that the electrons are going to throw through that connector you just made.
Yeah.
Don't worry about all that. What I'm asking you is, take part A and attach it to part B.
Yeah, let's say task oriented here.
Right. Right. And again, but nobody approaches it that way. If you're putting together a carburetor on a car, you want to understand how the carburetor works and what's important on, the steps you're doing to make sure that what you did is going to make that thing work. Because what you hate doing is, I'm one of those guys, I hate doing things twice.
Yes. Yeah, let's just do it once, especially up there.
Well, and
it took me a minute to get this suit on. I mean,
it took you a half a day to get the suit on and get ready to go do the job.
I do want to talk to you about this, but yeah.
Did you have any input into the glove design or any of the suit design as a tool engineer?
I have never had a completely different organization is responsible for the spacesuit itself.
Yeah, you just had to make it fit into the glove.
The suit comes along with a set of requirements if you want to work with it. Gotcha. So you have to meet that set of requirements in order for an astronaut to do it. And I mean, you got to have room for the glove, forces associated with if you're moving a thumb nod, how much force that thumb nod can actually, make it workable by the astronaut in a suit. But there was a complete, the spacesuit is honestly a spacecraft.
Yeah.
I mean, it is one of the great accomplishments in space is having that spacesuit, because, you build a vehicle and you have, fuel and oxygen and cooling and heating and all of that. And they did all this in a very, very small suit that goes around a person.
That's so cool.
And that suit has all its own onboard sensors, adjustments, so that the astronaut can do it himself if somehow he got cut off. It also has communications. Yeah, all that has to work in order for that suit to work. And that suit that we've got on space station is a very similar to what we used on the moon. So, I mean, it's been around for, 60 years, just like NASA now. And we haven't got there has not been a lot of changes. The next generation suits, there's a lot of work going in next generation suits. But in my world, the spacesuit was basically a constraint.
Yeah.
They're going to have to use it. This is what they're using. So you got to work with it.
Yeah.
And, but it's a marvel that they can actually send guys out in space, and they have their own vehicle to get around and do whatever they need.
It's so cool.
That part was, it's a very complicated part of the industry, but there are some companies that specialize in that. And they've all, we've worked with them whenever you run into problems, but we skipped over in a conversation about when, the things I enjoyed the most.
Yeah. We
were talking about the Columbia accident, but that spawned a huge amount of work to try and figure out how to fix the tile on the shuttle.
Yeah.
And there were several aspects of it that we focused on. When one of the first problems was, how do you get an astronaut underneath the belly of the shuttle?
Right. There's nothing to hang on to.
There's nothing to hang on to.
Latch onto.
And there's no way he can get there, and he can't just climb across it because it'll create more damage kicking it than he would to get him there. So we spent a very large design and development after the Columbia accident to create a boom. So the shuttle has a 50-foot robotic arm on it.
Right.
And it has an elbow in the middle. So what we were trying to do is figure out how to utilize that arm, but that's not long enough to reach to the underbelly of the shuttle.
Yeah, because it was only 50 feet, right? The payload bay is 15 by 60.
Right.
And
so
then the arm is only 50. It was only meant to operate and contract into the payload bay.
It was basically the crane for the payload bay.
Yeah.
But in order to get around the whole side of the vehicle and all the way to the underside, they needed more.
Yeah.
So they had several contractors trying to figure out a way to do that. The final solution was the arm is made by the Canadian Space Agency. So Canada made a 50-foot boom. So the arm flew on one side of the shuttle payload bay, and the boom fit on the other one. So when they needed it, they could put the two booms together. Now I had a 100-foot long boom.
Oh, cool.
With a joint at about 25 foot up. So that was enough to reach around to the bottom of the shuttle, and then you had this 75-foot windshield wiper.
Wow.
That could pan
and sweep the whole bottom out in any place that you needed it to go underneath.
And again, it's just a stick, right? So now we had to put an astronaut on the end of that boom and make him do the work.
Yeah.
So that was the final solution. One of the things that Boeing stuck its hat in the ring was to create again, this was only supposed to be used in the event you knew you had a problem.
Right.
This is how you fix it. So it was not going to be an every time thing. It was like, if I need to go out and do a one-time repair, how do I get there?
Damn.
So we developed a design that was an inflatable boom.
Oh,
because they didn't want to dedicate all this
cargo space, weight,
volume,
absolutely.
All this. You don't want to fly this 1,000-pound stick every
damn time
that you weren't ever going to use.
Yeah.
And so we said, well, let's come up with an inflatable
It's really
idea.
smart, though. Yeah.
It was, and it rolled up. It was relatively, it fit into basically about the size of a 55-gallon drum.
Okay.
Right. And then it would deploy out. And we worked out, there's a big industry out there for deployable like military tents.
Oh, okay, yeah. Or like the rafts on airplanes or something like that.
Or that same kind of thing. Space has gone into some of the inflatable vehicles,
HABs and things too.
HABs and things that you could do. So I mean, the technology was out there. We went to a company and they made tents. They made like MASH units for the military, and they basically roll this thing out, pressurize it. You got a building.
Damn, that's cool.
You go inside, you shore it up where you need to shore it up, and now I got a building.
Perfect.
And
it's water resistant.
It's all those things, right?
So,
I mean, and it was just a balloon, so they were available to change the materials. Mm-hmm. They worked with some Kevlar protection for micrometeoroid.
Sure.
You get thermal protections. You got layers and layers of this, but you had to still make it inflatable and small enough.
Yeah.
And we came up with this boom that was inflatable. It was about 18 inches, 2 foot in diameter. I don't remember. And we put this stainless steel cuff around it that you could basically squeeze on the inflatable to give you a rigidized work spot. And you could slide that cuff anywhere up and down this 60-foot boom wherever your problem was.
Damn, that's cool. Was that ever deployed?
Not in space.
Okay.
Right. But we actually.
But you could have if you needed to.
Well,
it was tested and ready?
It was tested for everything except actual flight.
Oh, okay.
So we tested the fixture in its fully deployed configuration to get through, thermal and mechanical and any problems we had with this cuff that was going along, because it had to be, sliding along a smooth surface. And does it hold? How does it hold? We actually took this boom and we actually took it underwater. Another interesting.
Nutribuoyancy lab. We're going to talk about it in the next episode, not this one. I'm going to have you back for a part 2.
But we took this, it's a balloon, and we're going, okay, no, how do we test this underwater?
Yeah, because it's going to float.
And so one of the guy who designed it basically said, oh no, that's simple. I said, and he says, we'll just fill it up with water. And I'm going, well, that's cool.
Son of a bitch. Yeah, that's why we keep you around, Larry. Nice job. Yeah.
And I just laughed because he used, I don't think it was even an inch. It might have been 2 inches of PVC.
Yeah.
Brought that PVC up out of the water about 20, 25 feet, something like that. And they just filled that tube, and that creates enough pressure to pressurize all the water inside that volume.
Damn.
So it's just water pressure, which is, but
it's brilliant, though.
Figuring out how to get the right pressure on that to simulate an air volume.
Yeah.
Right. And simulate the air pressure, but do it with water underwater. So you get the water in the pool that's pushing you from the outside, and you get the water from the inside through this water pressure system that just gives you the right differential so that it'll work perfectly.
Damn.
Like I said, little problems like that, right?
But little opportunities in disguise. But how cool is it to be solving challenges like that?
And
like that, you show up every day, you're just like either continuing on a project that's awesome, or you're starting a new project that's awesome.
Right. And so that was a very cool project to work on. Didn't go anywhere.
Yeah.
It turned out, like I said, Canada got the bid to put a second boom, and they flew that second boom on all the missions after Columbia.
Yeah.
And then at the end of life, we actually put that boom on space station.
What did it ever need to be deployed to repair anything?
We tested it once to repair something.
Okay.
And we actually used it once to go after something. So they didn't really perform a repair, but they did go and look at a spot, and actually in between all these little square tiles on the bottom of the shuttle, they usually use a spacer. Mm-hmm. And some of these spacers came out. So doing a camera inspection, they do a camera inspection with that boom.
Okay, that makes sense.
So you do a camera inspection first. They spotted something that they thought was a serious problem. They went out there and looked at it, and they pulled out the spacer and brought it home with them, but it really wasn't a problem.
Yeah,
it was,
and that's something they do on the ISS. Is what they used to before the shuttle program retired, was they would flip it over, and so the ISS could get a look at the underbelly.
Right.
And then also they had that issue of, I want to say it was Columbia, whenever it came back in, they knew something was wrong. I want to say they knew something was wrong early on, or they figured it out mid-flight while they were up there. So they pointed satellites at it and tried to get photos, but they were not able to determine anything based on that.
Right.
But having that Canada-arm go out and do a sweep before the ISS was up there that could do that.
Right.
That's pretty interesting.
And they did that after all the missions after the Columbia accident.
Yeah.
They would actually perform an inspection as part of ascent Before you got to work, you wanted to make sure there was no problems with the heat shields for return.
How long was it between when Columbia happened and the Canada Arm deployed? Because it was 2 years before you returned to flight. Not Columbia, Challenger, it was 2 years before you returned to flight. But because of the Columbia incident, how long before they were able to do that? When did that go into implementation?
We didn't fly again until we had that boom in place.
That's interesting.
And to Canada's, great support and effort to the program, that boom was made of very similar components as the shuttle arm.
Yeah.
So, and they were already designing a space station arm at the time. So they had all the right technology to and again, it was a very simple boom.
Yeah.
Right. One piece, same fittings as the shuttle robotic arm for launching and releasing and deploying. So, I mean, they had all the right groundwork in place. So again, they leveraged off of the shuttle arm design and created a new boom. Was the minimal cost, but again, the bad thing that the program didn't like is they had to suck up that overhead.
Right.
The cost to modify the other side of all the shuttles.
Right. To
put in all these features, to have these booms.
Yep.
To fly these booms every time.
The excess in weight, then you have to take off something else.
And it had to fit.
Yeah.
And
with
not,
whatever other cargo you wanted to take
and not interfere with everything that was already designed to work.
All of it for a safety protocol.
Correct. And but that was one project. The boom was one project. So another aspect that we did is we put a crew member on the end of this boom to actually do the work on the bottom of the shuttle.
Yeah.
Now, how do you know that you're not going to hurt the shuttle robotic arm by doing that? Because you just added a 50-foot moment arm to the end of this arm. You don't want to backdrive joints and start tearing up gears or mechanisms.
Snap off and
bad, all bad.
All bad, yeah, not ideal.
No, I mean, lots of bad things could happen. So we had to prove that wasn't a problem. Again, a small project I got onto was crew members work out of what's known as a foot restraint. So they click their heels into a plate that's like ski boots, right? Then you just kind of click your heels in, and then you've solidified your feet. So you got a work platform, and it's a standard piece. It's a standard tool for space station and space shuttle. So they've always had these things. So when you're working outside, you've got a way to secure yourself to structure and then be able to freely work, so you're not always floating around.
Yeah.
Well, they put one of these foot restraints on the end of this 100-foot boom so that you could, cherry pick an astronaut wherever you need to put him on the bottom of the shuttle.
Right.
Well, they wanted to make sure that whatever we had that astronaut do wouldn't backdrive the shuttle arm or break the shuttle arm or create more harm than you're solving.
Yeah.
So they asked us to build a foot restraint that actually had a load cell in it.
Oh, so you can measure the load.
So that you could, whatever that crew member's doing with his hands.
Yeah.
If it's a push off, whatever it is.
That's a great idea.
You could measure what it's doing to the tip of the boom, and then the robotic joints on the shuttle arm all had sensors on them, so they knew the feedback to them.
Right.
But what we didn't want to do was overload the shuttle arm.
Right.
By performing something, and it's simple physics. Yep. If I increase the moment arm, I'm multiplying that force by the moment arm.
Yeah.
And it's, if it's a pound out there, when I add 50 foot to it, it's 50 pounds. Yeah. And it's like, we got to make sure that we don't snap something when we're doing this. And but again, my small piece of this was to create the load cell.
That's so cool.
And put the load cell in space and let it collect the data.
Yeah.
So if I'm collecting data, I gotta have a power source. So we're using batteries, and during that project was the first time I learned about batteries in space. They're really not compatible. and lithium ion are the batteries of choice these days. And when you go and buy lithium ion batteries, AA batteries at the store.
Yeah.
Those are basically the batteries that we use on space station.
Really?
We certified a AA battery, and then that's what you use. If you need more voltage, you just put a bunch of them in series.
Huh.
But they all use the same cell.
Damn.
Because they took that cell, and it's not exactly the same as what you buy off the shelf, but I mean, they designed a cell, a small voltage cell.
Yeah.
And if you needed more amperage, more voltage, you just multiplied the number of batteries you needed until you got what you wanted. But if you used that cell, which was an off-the-shelf cell, you didn't have to go recertify the battery.
Damn.
Which is like, please give me that knowledge.
Yeah.
And, I'll go wrap 6 of them together to last for what we need to do, collect the data we need to do, run some small circuit board card that would collect the data.
Yeah.
Right. And then when we get back to the ground, we just take the card and it collected the data and we're done.
Damn.
But I mean, actually working with the battery, I mean, because lots of bad things. You don't want any leakage, you know, and
when they're coded for a reason too, but you guys couldn't have them coded.
You have to, again, they got to a design that they approved.
Okay.
So there was this AA cell that was approved for use. All the right materials, all the right, passed the high heat and the low temperature testing, and it never exploded, it never leaked, it never had a problem. And we would buy this cell by the lot, right? Buy 1,000 of them and just use them and keep using them until.
What's NASA doing? Little bunnies or copper tops? What are we talking about?
It's a completely separate name,
fair
but
enough.
I mean, it's
Radio Shack. Yeah,
it's not something you truly buy off the shelf. But they customized the design, and then when everybody wanted a battery, they bought those.
Damn.
And you could buy them 1,000 at a time.
Yeah.
And if you only needed 6, it didn't matter. You needed 100 to get through the testing.
Right.
Right. So I mean, it was much cheaper to just buy this lot of these cells and use them until you were done with the project.
Damn.
And again, I'd leave 500 on the shelf in bonded storage when we were done with the program. But we're going, well, there's a bunch of free ones for you now, or you already paid for those. So here, if you need them in the future, use them.
Yeah.
But that was a great project. I mean, the load cell was a great project. And
you did some work on the ISS batteries as well, right?
ISS. Well, when I started working the space station program, my company was responsible for the electric power system.
Right. Okay.
So, I mean, and you make that sound simple, but it's an external.
That's not simple.
It's an external system.
Yeah.
Solar cells and batteries.
Yeah.
And then charge discharge units and power distribution units.
Right.
And all that had to be assembled by astronauts.
Right.
And when it flew, however it flew, it had to be assembled by astronauts. And then it also had to be designed to be maintained by astronauts.
Yeah.
So everything had to be compatible with the astronaut, compatible with the suit, compatible with the tools.
Right.
Basically, simply, remove and replace type items.
Sure.
And I say simple, we push the envelope for simple, because one single battery on space station, and there's, I should know this, there's 48 on space station, but one single battery is about 18 inches tall, roughly 3 foot by 3 foot.
Okay.
So it's the size of a small chest refrigerator.
Yeah.
Right? And we attach those to space station with 2 bolts.
Holy shit.
And so when a crew member has to replace me, he just has to undo 2 bolts. He now has a refrigerator in his hands.
Yeah.
And he hands that off to somebody, because that's the dead one. Now give me a new one, and he puts that back in and he drives 2 bolts.
Damn.
But to get to that design end,
Yeah.
required an enormous amount of mechanical work to make it happen.
That
So
we are going to pick up on our next episode.
that's fair, but that was
Okay. Because I've got a bunch more questions, but we're just out of time.
But that's okay. The electrical part of the job was, to design that system, and included in that was the solar cells.
Damn.
So-
See, and solar cells we're going to pick up on the next episode.
Okay.
Did you have any additional questions for him on this one?
I do, but it's just a joke question.
Okay.
Did you include like a smoke detector sound when the batteries went out, so they had to go and find which one it was on the ISS?
I hate to say it, for the new design, we actually did have to design in a port that would allow gas to escape the container it was in. And that port, because it was lithium ion and because they could flash, if you know anything about lithium ion batteries, their failure mode is they burn up.
Yeah, a little bit.
So we did create a port, and the indication that battery had failed would be scorching at that port.
Wow.
You'd know it from the inside that it failed, that
Right.
it wasn't working. But you had to go out there, and they actually had a vent port that they would ask you to see if there's scorching next to it.
Oh, wow.
Wow.
It was,
But that would be a cool thing to do, to haze the rookie. Have a beep go off, and they're like, all right, guy, get out there. There's 48 of them. Go test them all. Go see which one's beeping, like your smoke detector in your house. That's hilarious,
Exactly.
Patrick. Thank you.
it's
That's hilarious. Well, thank you so much for joining us, man. Do you mind doing another episode with us here in the near future?
Are you telling me that we're already through an hour?
Yeah.
Goodness. All right. Yes.
It's it goes and it flies, and I have way more questions for you. We just are out of time for this one, so
All right.
we will definitely be doing this on the next one. Curt Carlton, thank you so much. Patrick, thank you so much for that banger there at the end. Good
Yeah.
call, dude.
Thank you.
We'll be back.
We will be back. And you guys can find us at Expanding Reality Podcast, I think. Yeah, on Instagram, Facebook. Then you can go to the YouTube and see this videoed there. Thanks again to Curt and Patrick for hanging out with me. I really appreciate it. And we will see y'all next time. You guys be good to each other. Get out of the left lane. Be nice to everybody. All right.